Everybody, here we are, chapter 4, exponents and radicals. This is 4.1 squares, square roots and cube roots. So a few notes before we get started, and I put all the definitions in blue. I typed them out so you don't have to read my printing. So if you could write out all these definitions, and then I'll kind of explain them as we go, and if you need me to pause for more time to write, I can do that. So the perfect square is a number that can be expressed as the product of two equal factors that are whole numbers. So our positive counting numbers like 1, 2, 3, 4, 5. So for example, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, 4, 9, 16 are all perfect squares because they're the product of two equal factors, 2 and 2, and 3 and 3, and 4 and 4, that are whole numbers. And if you're in my math 8 or 9 class, I sometimes call these celebrity numbers. The square root is one of two equal factors of a number. So, in our previous one, it would have been, 2 or 3 or 4. The square root of 4 is one of these two equal factors. The square root of 9 is one of these two equal factors. The square root of 16 is one of these two equal factors. So square root of 4 is 2. Square root of 9 is 3. Square root of 16 is 4. We also, we don't need to, a square root can also be a decimal. We can have, for example, the square root of 8, which is going to be pretty close to the square root of 9. I think it's I think it's 2.83, something like that. So it can also be a decimal. Perfect squares are, a specific kind. Square root can be numerous things. A perfect cube is a number that can be expressed as the product of three equal factors that are whole numbers. So our positive counting numbers, but now three of them. 2 times 2 times 2 equals 8. 3 times 3 times 3 equals 27. 4 times 4 times 4 equals 64. And the cube root is one of three equal factors of a number. So in this one, the cube root of 8 is one of these equal factors. The cube root of 27 is one of these equal factors. The cube root of 64 is one of these equal factors. So we can show the cube root. You have to put it at the index. This is called the index right here. So you put a little 3 there. If we don't have anything, it's assumed to be a square root. So you put a 3 there as an index to show that it's going to be a cube root. The cube root of 8 is 2. It's one of these equal factors. The cube root of 27 equals 3, just one of those equal factors. The cube root of 64 is 4, just one of those equal factors. And prime factorization is a process of representing a number as a product of its prime factors. Remember, a prime number is a number that's divisible only by 1 in itself. So, for example, if we represented 24 by its prime factors, it would be 2 times 2 times 2 times 3. And I'll show this a little bit more. We're going to do a prime factorization tree. So we can show you the process by which we get to here from here. I'll show you that in a little bit. So some more info on square and cube roots. Square roots are related to the area of a square. So if I have a square like this, we say the area equals 169 centimeters squared. If we wanted to find, the area, we would do side or side length. I like to show side length, SL times SL. So if we want to do the area, that would be side length times side length. That's equal to side length squared. And if we remember our inverse operation. So if we wanted to get rid of this squared, we would have to do the inverse of that. So remember this part right here. Hang on a second. Remember the side length squared equals the area. If we want to get back from that, we have the area and we want to get back to the side length, remember we need to use an inverse operation so that the square root and squaring something cancel each other out. So if we have the square root of the area, that equals the side length. So if we want to find the side length here, we can go square root 169 equals 13 centimeters. That would be the side length of this square. And the cube root is related to the volume of a cube. So if we have a cube like this, while I'm recording this at home, you might hear my cat. We say the volume is 125 centimeters cubed, and we want to know the side length, side length, side length. We know that the volume is the side length times the side length times the side length, or side length cubed. And if we want to go back, we have the volume and we want to get to the side length, we can take the cube root of that. So we can go the cube root of that, minus a little bit. So if we want to find the side length, we have the volume of this cube, we can do the cube root of 125, and we get 5 centimeters as our side length. Okay, so let's do some questions. Determine whether each of the following is a perfect square, perfect cube, both or neither, and justify your choices mathematically. With 121, if we wanted to, decide whether this is a perfect square, we could show this as a diagram. If we wanted, we could try to draw a square with side lengths that are equal. I know if I wanted to have 121 in the middle, I would need to have 11 on each side. I don't know why you would necessarily show it like this with the diagram, but here we are. This is what the textbook gives us. So yes, we can make a square with side lengths 11 that equal 121. So that's a perfect square. So yes, on the perfect square. Is it a perfect cube? You could kind of guess and check on this. So let's see. Let's see what like 4 cubed is. 4 times 4 times 4. I know that to be 64. And 5 cubed, 5 times 5 times 5. I know that to be 125. And so no, 121 doesn't fit in there, doesn't nail one of those ones. So not a perfect square or not a perfect cube. So just a perfect square, not both, not neither. For 729, I'm going to show you prime factorization. So we're going to break this down to the point where we get its prime factors. So let's do a prime factorization tree. We're going to split this into as many prime factors as we can. Let's just kind of break it down into some other smaller, more manageable numbers. I know that 3 goes into 729, and here's a trick. 7 plus 2 plus 9. If you add the digits, that's 18. If this is divisible by 3, the big one is divisible by 3 as well. So I know I can take out 3. And then I know, I think it's 243. Let me just check on my calculator. Because it goes in 200, then another 40 brings us to 720, and then 3 more. Yeah, I feel confident about that. Now, this is already a prime number, so we can just bring this one down. This one's done. So that's our first kind of fact right there. 243, if we do the same method, if we add up the digits, 2 plus 4 plus 3, that's 6, that's 9. 3 goes into there, so I know 3 can come out again. Come here, kitty. Okay, and it can go in there 200 and what gets us to 240? Let me just use my calculator. Oh, not my camera. 240 divided by 3, 81. There we go. So now we got 3 times 81. That we can break down into a 9 and a 9. That can break down into a 3 and a 3 and a 3 and a 3. So now we have the prime factors. 3 times 3 times 3 times 3 times 3 times 3. A bunch of 3s. So how we can determine now if this is a perfect square and if it's a perfect cube is if we can separate this into two equal groups, then it's a perfect square. So can we? Yeah, we can. We got 3 times 3 times 3 times 3 and 3 times 3 times 3 times 3. So we separated this into two equal groups. That's 3 times 3 times 3, 27 times 27. That equals 729. So we split it into two equal factors. And then we can also figure out if it's a perfect cube if we can split this into three groups of equal factors. And it looks like we can. If we have 3 times 3, and then we would have another 3 times 3, and then another 3 times 3. So we could have this as 9 times 9 times 9, or 9 cubed, and we would get 729. So this is both. We can say both. And the last one, I don't know, several methods. We use a diagram, we use prime factorization. How about we just use the calculator? Let's see. So let me pull this over here. Let's just see. If we do the square root, do we get a whole number? 356 square root. No, 18.86. So let's do that. 18.87, I guess. And now let's try the cube root. Let's just do this in our calculator. 356 equals 356. Let's do cube root 7.1. So no, neither of these are a whole number. So this is neither a perfect square nor a perfect cube. I think that's probably, the easiest method, but if it asks you to do a different way, use prime factorization or show a diagram, there you have it. The next one is a little bit of a review, squaring and cubing integers and rational numbers. So if you're squaring or cubing a negative number, you must include the negative sign of the brackets included. So if there are no brackets, then you square or cube the number and then put the negative sign in front at the end. So for example here, 6 squared, this is, I'm going to use my blue, 6 times 6 equals 36. Here, our base, if you recall, the whole thing is called a power, and this number that's being squared is called the base. And since the negative is inside the brackets, it gets included as well. So we have a negative 6 times a negative 6 gives us a positive 36. And this one, our base is actually positive 6. So we have the negative on the outside, and then we have 6 times 6. So that means we have a negative and then a 36. Okay, so the brackets are super important. I know you did this last year in Math 9, so make sure you're paying attention to the brackets. And the same goes for cube roots. Here we have 4 times 4 times 4, 64. Here, the negative's inside the brackets, so it's going to be multiplied as well. So negative 4 times negative 4 times negative 4 equals a negative 64. So negative 4 times negative 4 is a positive 16, and then positive 16 times a negative 4 is negative 64. Now here we have a negative, and then on the inside 4 times 4 times 4. So that's going to give us the negative comes over, and the 64 stays, so negative 64. And here I showed it all. I had to insert the whole equation. But for example, here's what this looks like. So 2 over 3 cubed is, I'm going to show it as well. It looks like this: 2 over 3 times 2 over 3 times 2 over 3, which can also be showed as 2 times 2 times 2 over 3 times 3 times 3, which is 2 cubed over 3 cubed. So that's what that looks like, kind of all written out. So you can kind of distribute this 3 inside, which I think you did in your review. And here's square rooting and cube rooting rational numbers. If there's no number in front of the root sign, which I think I mentioned earlier, no index shown, it's assumed to be a square root. So it's assumed that there's like a 2 there. And so here's a kind of property of square roots. The square root of 9 over 25 is equal to the square root of 9 over the square root of 25. So hi, everybody. I think I got cut off, but I think I'm right here. Another property of radicals is that here we go. The cube root of 64 over 343 is the same as the cube root of 64 over the cube root of 343. You can solve those and keep it as a fraction, so 4 over 7. And then these ones I want to show, there's some questions like this in the textbook, and I just want to make sure you know how to do these. These ones, I mean, there's two ways. I mean, both are going to be true, that you could keep this as cubed root and solve inside 8 times 64. Let's see my calculator. 8 times 64 equals 512. And then we do the square root of cube root of 512, 8. But it's also true that this is equal to the cube root of 8 times the cube root of 64. So 2 times 4 equals 8. So I feel like, this is kind of like helpful. It uses smaller numbers and is more manageable without a calculator. For this one, it's also true, just similar to right here, that this is the same as the cubed root of 8 over the cubed root of 125. So that's equal to 2 over 5. And these ones that use, that have like an x squared. So remember what a cube root is asking you. It's asking what times itself, question mark times question mark, it's the same question mark, equals 9x squared. So you can think about this as well. The square root of 9 times the square root of x squared. So the square root of 9 is 3. And if we have the square root, remember, of something being squared, it cancels that out. And we are left with 3x. You might recall from polynomials that if you multiply, say if you did 3x times 3x, you multiply the top ones and multiply those. So you end up with 3 times 3 is 9, and an x times an x is an x squared. So that's how you do those ones for the textbook. Thank you so much, and I'll tell you what questions I want you to do.